Okay, good afternoon, everyone. My name is Edward Bortnikov. I work for YAO Labs, and today I'm going to speak about a research project we are running there and hoping to productize. This is joint work with my friends with YAO Labs in Israel and in Champaign, Illinois. So the topic today is going to be block management as a service, which is the concept that that we use for scaling the HDFS name node. So the motivation is fairly simple. The expectations from the Hadoop grids to store and process more data are growing all the time. We have new data sources. Recently, people started doing massive image processing and machine vision algorithms based on Hadoop. We're dealing with larger collections of data, and we're trying to build to bring more data sets together to co-analyze them. And in that constellation, our requirements for both storage and compute are growing all the time. So a 10,000 node cluster is more or less a common requirement, at least in our company. And 100,000 node systems are envisioned. However, the harsh reality is very different. Is a 5,000 node cluster is very hard to build, and 10,000 node cluster is next to impossible to build. Okay, so the goal of our talk today is trying to answer why and what can be done about that. So the key point here is, of course, that the system that you build is as scalable as its core platform services are. So, for example, there was a huge performance bottleneck in Hadoop scheduling as long as the Yarn architecture didn't come and solve it with the distributed approach to resource management and scheduling. So today we're going to speak about a different major bottleneck in Hadoop systems, which is the HDFS name node, the Hadoop file systems metadata service, and actually it's a foundation service for all the other middleware that is part of Hadoop's technology stack, like MapReduce, HBase, Spark, you name it, everything. So just a short recap about how HDFS works. So in HDFS, we have two kinds of creatures. We have multiple data nodes that are basically just storage space for storing data. They don't control how this data gets stored on HDFS. And there is a name node. And that name node is actually a server that runs two kinds of information. One of them is a POSIX-like hierarchical file system, and the other ones is the block information. So each inode is a collection of blocks, and these blocks are replicated for high availability and performance. And they are scattered across the data nodes in the cluster. And in order to be reliable and survive failures, the name node runs its write-ahead log, which is called edit log, where all the changes to both of these data structures are registered. So there are two kinds of protocols that are running in the system. One is the one driven by the clients. The metadata and the data accesses are split, so the clients go to the name node to fetch the metadata, and once they know where each piece of data, where each block resides, they go to the data nodes for the data path operations. This is good because this separates the metadata and the data path. So the other protocol that is running in the background all the time is processing the block reports that continuously arrive from the data nodes to the name node. Their heartbeats, and they report all kinds of information about which block replicas are allocated where, and this and the replica health. And this enables the name node essentially to figure out that certain inodes are either blocks are either over-replicated or under-replicated, and run the replication accordingly. So the good things about this design are that this is a memory speed server. Everything resides in RAM. But on the other hand, we have two major bottlenecks. One major bottleneck is the RAM footprint, because putting everything on a single server obviously puts a lot of pressure on RAM. And the other one is throughput, because it's very much reliant on the concurrency control inside that server, since it's serving clusters of thousands of nodes. So the high-level picture is as follows. We would like to work in both directions, both footprint reduction and throughput improvement. And in this talk, we are going to focus on separating the file system and block management, and we have a prototype with Yao for that. So this is the first step in the direction, splitting the two services to run and scale on separate hardware. The second step would be the prototype that has been implemented at Hortonworks, which implements swap space or cold storage for file system metadata, since the data that is stored on Hadoop grids becomes cold very fast, and it doesn't make sense to really store everything in the main memory. So the other optimization is a throughput boost, and we have a different project in that space, but it's a little bit premature to speak about that. In a nutshell, it's about redesigning the name node to be an asynchronous lock-free creature, but maybe we'll have more to tell about that at Hadoop Summit North America later this year. So just a small zoom in. As I said before, the name node maintains the Unix file system tree, and it has inodes for files and directories. And each file is actually a collection of blocks, the block info object in Hadoop, and each block has a bunch of replicas, and all that resides on the name node server. So in fact, we have two services that compete for resources within the same process. So they compete for the RAM space, because we have both file system and block metadata. And swapping of this parts of this state to disk does not really work unless you really build a very intricate caching system for that data. And the reason is that the block reports keep arriving from the data nodes all the time, and there's basically no locality in accessing the data. Every single piece of block information is touched. The other thing is that they compete for the CPU, although not as much. There are file system calls on the one hand versus the block reports and replication on the other hand. So this is the same second type of competition. And here's a bit of statistics about how the memory is actually used. The RAM is split in different ways between files and blocks depending on the file to blocks ratio. If we have smaller files, we have a smaller portion of RAM allocated to blocks and replicas. But as you see, in both cases, most of our memory is not the fixed overhead part. It really is split between these two major types of information, the inodes and the blocks and the replicas. In our applications at Yahoo, small files are actually a more widespread case. Most files tend to be small because customers want to achieve maximum I/O parallelism. So that's the picture in the reality. So from the scalability point of view, we would like to split those two services to scale them separately on different hardware. So from the file system perspective, as we saw, it's a potential for immediate capacity growth, something like 250%, and it's also a prerequisite for further optimization. So if you implement the cold storage optimization for the cold files, you can basically scale as far as you wish and remain memory speed almost 100% of the time. But it doesn't make sense to do this optimization as long as blocks are not removed off the name node, because as I said, there is no locality in accessing those blocks. So the nice thing about block management is that it's really easy to scale because it's a flat space. It's not hierarchical. So at the extreme, we could even think of pushing this service all the way down to the data nodes, so that part of the data nodes would also run the block management service. So one more thing is that a standalone block management API is a nice abstraction on its own right, because there are applications like NoSQL databases, HBase, for example, that really don't need a Unix file system abstraction, but that's not the focus of this talk. If we want to do this thing for real, we need to think about issues like security, for example, built in the block management system, and for now it's just a performance thing. So there are also challenges with this approach. So, for example, the backward compatibility of the API requires, of course, an extra network hop between the name node and the block management service. There are different implementation options. I'll demonstrate two of them. But in both cases, the implementation complexity is increased because it's no more the same process where all the data lives. So these two processes might have different life cycles, and new failure and recovery scenarios emerge. But I'll say a few words about how those can be mitigated. And one more thing not to neglect is the deployment complexity, because we have a new service to configure and run here. So in our work, we're following the same a bunch of simple design principles. Like we are, in the first place, of course, we need to take care about correctness, scalability, and performance. It's very important for us to be backward compatible both at the API and the wire protocol level, and recovery should be simple. So those of you who'd like to follow the discussion, it's on the Jira 5477. And here are the ideas that are being discussed. Those are the design alternatives. So design alternative number one is having the block manager as a completely independent service that has its own persistent state, which means that it's not reliant on the name node in any way for handling the block information. So The blocks are grouped in block collections. Each block collection is an abstraction that stands for a single inode, and the only connection between the two services is the reference by inode ID. So the block manager, as I said, hosts all the block and replica information, and it also runs its own edit log. So the advantage is the clear abstraction. It's easier to build an independent block management layer on top of that. And the challenge is that you really need to maintain the persistent state. You need to split the name node's edit log and to run a separate edit log in the new system. The second approach is more incremental. It speaks about leaving the name node responsible for running all the persistent information, and the block manager is volatile. So it gets its state from two sources. It gets the information about the blocks from the name node, okay, which is different from the previous design, and it gets the information about the block replicas from the data nodes through block reports. By the way, for the data nodes, it's completely transparent. The protocol doesn't change, and they're not aware that they're actually talking to a different entity. So the advantage of this approach is that the implementation is incremental. We need to do less things on the persistent log management side. But on the other hand, the block manager service becomes more reliant on the name node, and some recovery scenarios also become messier. But this approach works as well. So summing up the potential benefits of each approach, of course, if we have a persistent block manager, we can completely offload all the information from the name node, and the benefits are larger. But still, if we have a volatile block manager, the savings can be significant, and they open the way to yet larger savings in the future through the name node optimization. So, as we said before, the block space is really flat. So it's very. Oh, is the percentage of the used RAM. Okay, so the block space is flat, so it's very easy to scale it out on different machines. So block managers are actually logical entities, and they can theoretically be even pushed to the data node machines. Scaling the block management out actually reuses an abstraction that the block pool abstraction that has been introduced with name node federation, which means that the space in the data nodes is partitioned into block pools, and these block pools are managed by different entities. So nothing changes for the data nodes, but these entities just swap identities. In contrast with the name node federation, we have here a sharded or federated block manager, each process managing part of the block space. Okay, so obviously there are many challenges with the distributed execution, and each part can trigger a flow that either reads or writes to parts of the file system or block metadata. Well, we have basically two kinds of flows. One kind triggered by the client API calls, and this is the second kind triggered by the block reports. And in the centralized implementation, there is a very simple way to enforce atomicity of these operations. There is a single global shared lock that covers all the operations. Write operations take it acquire an exclusive lock, and read operations acquire a shared lock, and everything is nice. But of course, this approach will no more work if we'll try to preserve it in a distributed environment. So let's see what happens. Suppose we have two requests here of two client requests, each trying to add a block to a file in a completely different part of the file system tree. So if one of these requests acquires an exclusive lock, the other one cannot make any progress despite the fact that it works on a completely different file. And the reason is that this approach works okay as long as you work in a single process, and sometimes having a single global lock is even beneficial. But when you have parallelism, it just cripples the RPCs, and you cannot work with that. So the alternative to that could be fine-grained locking, which is one of the things that we've implemented. So if you have these two requests, actually what you need to guarantee that the file is not being removed either on itself or as part of a higher level directory when it's being operated on. So there's no real contention here. So what we can do is we can acquire an exclusive lock to the modified object itself, and we can acquire shared locks all the way to the root, which is fine. So now we are able to issue multiple RPCs in parallel. So, and this is not very unexpected. We have simulated a mix that has like 3/3 of 75% of get block locations requests, and the other part is create file requests, and this is more or less what we get. We see that the first global lock approach clearly does not scale. But the interesting question here is whether we need the locks at all. Okay, in general, holding locks across RPCs is considered a bad practice. Okay, these RPCs should not take too long a time to execute, and however, in the high percentiles of things can really get stuck, and if some request gets stuck in the block manager, the entire parts of the file system tree will become inaccessible for changes. So many things can impede progress, like spurious delays and process failures, and we need some unified approach for handling these kind of failures. So what if we assume a different kind of thinking? What can we live without distributed locking altogether? Okay, and it turns out that we can live with this approach because this is a very specific application with very specific requirements. So suppose that we are prepared to live with transient state discrepancies. Okay, I'll explain what I mean in a moment, as long as they don't lead to any data loss. So, for example, we can tolerate the case where there are some blocks that are managed by the block management system that do not belong to any inode. Okay, so clearly there is some inefficiency here, but this kind of inefficiency can be fixed in the background without burdening any real-time traffic. Okay, so it's a question how we handle it, and it really will take me a bit longer to go into the technicalities here. It's basically the question of the order in which you do things. So when when you create a file or add a block, you at first do whatever changes you are supposed to do in the block manager, and you create the blocks there. So whenever the information is created there and it still doesn't exist at the file system level, you can the system can experience a crash, or it can experience an RPC timeout, and the whole operation will fail. So there is some discrepancy. However, nothing bad has happened at the moment, except that the block manager has wasted some space for allocating a new block that is not really used. Okay, so we can fix it through background communication between the block manager and the name node. Okay, and of course it's similar to the situation when we have different discrepancies in the picture between the data nodes and the name node in Hadoop today. That these discrepancies can emerge from client failures, and so the name node and the data node can for a while have a different picture of the status of a particular block. So these discrepancies are resolved in Hadoop today through generation timestamps, genstamps. This is a mechanism that is used to break symmetry. So think about that in a way that these genstamps, the same genstamps, will break the symmetry between the name node and the block manager as to the status of the blocks that have become temporarily orphaned. Okay, so I don't really have time to go into the whole protocol and the theory behind it, but basically it's doable. So okay, and altogether it's a neater, healthier approach to recovery, because it lets us deal with transient and persistent failures in a uniform way. There is a chit-chat that's going on in the background between the two services, and we can fix the state through this chit-chat. Okay, moving on to the service bootstrap. So for the name node, it remains the same. The name node boots from its own edit log. The block manager depends which design we pick. The first, so in the case of a persistent block manager, it's a self-sufficient service, so it boots from its own log. Okay, and in the volatile block manager design, it is dependent on the name node. So it really cannot function without the name node being around. So we have one more protocol here in place, and this increases the complexity a bit. But basically, the bootstrap protocol in that case remains the same as the chit-chat that runs in the background all the time during the normal operation. So for block replicas, everything remains the same as it used to be before. The data nodes speak with the name node with the block manager processes. They just don't know that this is what they do. Okay. High availability is similar to Bootstrap. It's possible to run block managers in a similar way to high availability in a similar way in process pairs, like we do run the name node processes. It's just a matter of faster recovery than just the cold recovery from the log, because the backup process can be listening on the log, and thus it will take it less time to get up to speed. Okay, last point is which is the most complicated part of the picture, supporting the name node federation. So the block managers don't really care which part of their data is owned by which files. So they can be shared by federated name nodes in the same way that in name node federation, the data nodes have been shared by different name nodes. So there is no problem with the multiple name nodes using the same block manager. And the nice part of it is that once we support federation, any data movement between the name node servers actually does not touch any bit of block information. Okay, so we can shuffle subtrees around, and they keep pointing to the blocks that actually reside in a different service. Okay, these blocks are consistently hashed in some way to the block manager processes, and everything's fine. We can even envision the situation in which in the name node federation there is no fixed partitioning of the namespace between multiple servers, and then, for example, if you want to move a part of the file system tree to a different subtree, say from /user to /backup, you just detach it from the /user parent tree and leave it at the same name node process, and just register in some look-aside service that it belongs to the different part of the namespace. But this is part of a different discussion. It just comes to show that operations of moving stuff either within the name node or between different name nodes can be made ultra fast because they do not deal with blocks at all. Okay, so let me summarize here. So HDFS has hit its scalability limit in its largest installations. We are very close to hitting the wall. So the major name node redesign is required. This is not the only redesign. There are alternative designs out there, like, for example, the giraffe system that Konstantin has suggested a while ago. We have described a block manager as a service approach, which is a major performance feature, which provides optimizations on its own right, but is also a prerequisite for future optimizations and an attractive low-level API abstraction going forward. And there is a community discussion. It's not finished yet, so please Hadoop committers feel free to chime in and say what you think. So and we had a prototype implementation for that at Yellow, and it really works, which is nice. So here I want to thank you, and I'm ready to take questions. I need to understand better what you mean by state sharing.
Okay, for example, state mode. There's a lot of code where you check state mode.
Okay.
Yes, you're always checking state mode, see the name of the state mode.
Okay.
And you will do that with block manager. You do the name.
The block manager, if it becomes a persistent independent service, you would need to have the same type of logic in the block manager as well.
If you get my point, that this is stating that both the name node and the block manager need to be in agreement on whether the service as a whole is in state mode. If the agreement of
Right, and it's enough that and it's enough for one to be to think that it's enough for one of them to fail that agreement, obviously. So is it?
You're going to have funny situations if block manager is safe mode and name mode is safe mode and operating system again.
That's correct, but for that you need okay. I see what you mean. That's right, but you know when this is part of the bootstrap solution in which the name node and the block manager or the different block manager processes need to have a handshake anyway. So it's I'm not sure that we really need a 100% an abstraction of 100% safe mode state here. For example, you can serve some metadata for reads from the name node while about file status and things like that without really allowing adding new blocks or getting information about block locations, etc. So the name node can be operational. But part of the data is not accessible. I'm not sure.
You change the semantics of safe mode.
That's correct.
And what about then by partitioning or sharding block manager? If you don't replicate the state, it increases the probability.
So again, that depends on whether the block manager is volatile or persistent. So if it's volatile, it's it can completely restore its state from the other services. The block locations will come from the replica locations will come from the data nodes, and the block information will come from the name node. So the state persistent state is maintained elsewhere, and then if we shard, and then if each instance of the block manager will have its own log, this becomes the local problem for that instance to restore its state. Right. So what kind of okay, the question would be what kind of cross-partition operations do you envision here? The only thing that we really thought of is the concat operation between multiple files, okay, which is really a boundary case. The other in the other cases there is no partitioning at all because no sharing at all because we partition at the block collection level, but not at the block level. Okay, so you don't the RPC does not reach out to different instances of the block manager. It just goes to a single instance for working with a single file. So the picture might be a bit less balanced, but the statistical multiplexing will work. Basically, it's good enough for sharing. So for all practical purposes, concat is the only case that really needs handling here, and it can also be solved with this eventual consistency approach. It depends on the order in which you do things such that you never lose data.
So traditionally in HDFS, block management wasn't persistent. It was simply recording where things were. That was the main point of it. And the inode itself would, of course, have information about what blocks were in the inode. So it seems like you're taking an approach more where the block manager actually has the inode information. That's what I'm getting from this non-volatile, whatever you call it, persistent.
Yes, so it's just the information about what blocks are there in the inode, and there are a few attributes that are persistent. For block. And so this just moves off to a different log.
But to me, this seems like you're leaking more HDFS details in the block manager, right? I mean, let's say that I'm HBase and I just want to create blocks in places. I have the block manager and open. I don't have inodes. I don't have listed blocks necessarily.
That's correct. So what HDFS would care about is creating a block collection, and I don't have a very clear picture of whether block collection is a good abstraction for HBase as well. It might be, because if you have large regions, for example, that you'd like to manage as block collections. In fact, there's one more feature that is being talked about that is even a level above block collections, which is file affinity. If you want to co-partition two data sets together, and they are different HDFS files. It's not the name node state. It's more like the logic of.
It is the state, right? The blocks that are in the file is different. So go ahead.
So it's just a grouping of blocks, right? So we know now that we create grouping that we want at the same time. If you put the right abstraction, it's not that bad. It's not the state application. And actually people more than if they want to particular group. Yeah, and that probably
And by the way, in enterprise storage, for example, in SAN, you can in certain protocols you do have this kind of abstraction, and it serves exactly the same purpose.
Well, like I said, what I'd like to see is a comparison of design where we just put the existing block manager in a separate process, which is not volatile, has no state, basically just receives block reports. That's what I thought this was going to be.
So this is the second. I'm out of time, by the way, and maybe we could take this discussion offline. But I'll take time to answer that question. So basically, this is this design. Okay, it is you can implement it.
Okay, but I still
Yeah.
I know that you go across the boundary.
It's just the reference. It's just the reference. Don't call it inode. So so why should it? Why should the block management care about inode semantics if it's just a reference? You see, it knows nothing about the inode attributes. They don't get replicated downstream.
Yeah, I understand that, but still, now when I'm changing something, I need to update it on both sides. So now I have.
Can you give an example?
Well, let's say that I'm adding a block to file.
Okay.
So, what does that look like concretely?
At the inode side, all you need to change is access time, which is not a critical attribute.
Which gets changed first?
The block manager gets changed first. The quota. That's correct. That's a very good point. But quotas can be actually managed lazily. You can say in advance that you've used up some of the quota before calling the block manager. Yeah. So you do a conservative approach. So if the operation fails, it fails, and then you get that information at sync at some point. Let's take the rest of it offline because we're out of time. Thank you.